So, in this video, we will be explaining evanescent waves. The part of evanescent wave that we will be covering is actually the evanescent waves that are formed due to total internal reflection. There are several other evanescent waves which we will only partly mention. So, before that, let us consider the equation of a plane light wave. So, how do we characterize a light wave? It has the magnetic field component and the electric field component. And we generally use the electric field component to actually signify a light wave. So, as you can see, the equation of a plane light wave has been characterized here by the equation E is equals to E naught, e raised to the power I, k dot r minus omega t, where k is equals to kx I cap plus ky j cap plus kz k cap, and r is a normal radial vector. Now, for a general propagating wave, the equation is this. However, when this light wave is restricted to a particular plane of diffraction and reflection, let's say the xz plane, then the equation reduces to this. In this equation, we have ky equals to 0, since because the plane is actually the xz plane. Now, what happens if one of the components of k becomes imaginary? That is, kz is equals to alpha I. Here, first of all, we need to understand the importance of k. K actually signifies the propagation of a particular wave, right? So, when we have a particular imaginary component, it means that the wave actually becomes lossing in that particular direction. If we have the value of k to be real, we have the propagation constant, we have a propagation in that direction. However, the imaginary value of component leads to a decay of the wave amplitude in that direction. Now, if this decay is in the direction of propagation of the wave, then the wave loses energy and we see damping. On the other hand, if the direction of decay and the propagation are mutually orthogonal, which we will see in evanescent waves, then we will not have any loss of energy and the energy is conserved in the direction of propagation. So, what makes K complex? For this, let us consider total internal reflection. What is TIR? TIR basically happens when the angle of incidence in the denser medium is greater than the critical angle. Now, what happens is, we must have been taught in class 11th and 12th that when TIR happens, there is no wave that is propagating in the refracted side, right? In the rarer medium, that is. But that is not true. To come to the exact idea, what happens is that when we have TIR, we do have a refracted wave in the rarer medium, even when the incidence angle is greater than the critical angle. And this wave is actually different from a normal wave in that it is actually an evanescent wave. So now, what is an evanescent wave? Let us first of all consider the few equations that we will be going through. Now, as we can see in this slide, we have this diagram where we have refraction going on. Now, when the incident angle, that is theta I, is actually equals to theta c, theta t becomes 90 degree. That is, the refracted ray actually goes on along the interface. Now, when theta I becomes greater to theta c, what we have been told is that there is no refracted ray. But actually what happens is, mathematically, if we see, sine theta t is equals to n1 by n2 sine theta I. This equation actually comes to the Snell's law, which says that n2 sine theta t is equals to n1 sine theta I. Now, when sine theta I becomes greater than sine theta c, sine theta t, which is represented by this equation, becomes greater than 1, since n1 is greater than n2. This leads to the equation E is equals to E naught, e raised to the power I, ktxx minus omega t, e raised to the power minus alpha z. Now, I'll tell you why we have separated the kz component. Coming to the next slide, components of k. So, omega t by kt is equals to c by nt. This is the general equation related to the velocity and the frequency, which then relates kt is equals to omega n2 by c. This is basically the kt for any wave that is traveling in n2 medium, right? Now, ktx, which is the x component of kt, is kt sine theta t, which is normal vector algebra. Also, This also shows that ktx is greater than kt if theta t is greater than theta c, since we have already proved that sine theta t is greater than 1 when theta t is greater than theta c. Ktz, on the other hand, is equals to kt cos theta t, which also comes from vector algebra. Now, since sine theta t is greater than 1, cos theta t, which is equals to root of 1 minus sine square theta t, comes out to be complex. Therefore, ktz is equals to I alpha, where I is iota, and where alpha is equals to mod of kt cos theta t. Therefore, we get a complex ktz. So, what have we learned from the slides until now? That ktz is imaginary when theta I is greater than theta c. Otherwise, we would have had this as the transmitted wave. Also, when theta I is greater than theta c, ktx which is equals to kt sine theta is actually greater than kt. So ktx is real, whereas ktz is imaginary, where ktz is equal to I alpha and alpha is equal to mod kt cos theta t. So this here is the given this thing which shows the formation of the evanescent wave. This here is the evanescent wave in the x direction, where ktx being real, this demonstrates the propagating part, whereas this demonstrates the decaying part in the z direction. Of course, the angle is theta I greater than theta c. So now the primary question that arises is there energy lost in TIR? Well, as we mentioned, since the direction of propagation is the x direction and the direction of decay is perpendicular, that is in the z direction, there is as such no energy lost. What happens is that the total energy is actually conserved and the energy only decays in the z direction. It can be understood, let's say, as various beams which have their amplitudes decaying in the z direction. So let's say this is what happens when we see this. So basically this is an evanescent, it can be modeled as an evanescent wave which is propagating in the x direction but decaying in the z direction. Also, so the misconception that we always had in class 11th or 12th was that we do not have any energy traveling in the rarer medium, but this is not true, because as I told you, the evanescent wave actually does carry energy, and it is this portion which leads to a decay, but it does not lead to a decay in the energy. It leads to a decay in the amplitude, which can be modeled in this way. So the common misconception that we have always had is that the total incident energy is actually equal to the total reflected energy in TIR. But this is not true. What happens is that the total incident energy in the z direction is equal to the total reflected energy in the z direction, since I already told you that there is no energy flowing in the z direction. However, this cannot be true for x direction, as we already have a propagating wave in the x direction which is refracted and which carries energy. So the energy of incident is equals to energy of reflected only for z direction. Also, all of this that we have modeled is actually for infinite media. If we have a finite media, let's say then in this case, not only do we have refractions and refractions at the various interfaces, we also have the formation of the evanescent waves. So in order to actually satisfy all the boundary conditions, we need to have evanescent waves along with these refracted and reflected components of the light. So I think that completes it. So coming to the uses of these evanescent waves that are produced, that are moving across the interface, right? So it is actually used in wireless power transfer. Now this kind of evanescent wave is actually different from that produced in TIR, but it is still an evanescent wave. So for this, we have the concept of far field and near field. In the near field region, the waves are actually bound to the antenna and are decaying, and hence are evanescent waves. So what happens is, if we can bring that if we can bring two coils in the region such that their near field actually resonates with each other, then we have significant energy transfer and it gives wireless power transfer. It is also used in RFID devices and contactless cards which use evanescent waves. These evanescent waves are confined in the near field so that there is no problem of stolen energy, since it is concentrated in a small region and hence can be used for the purpose they have been designed. Also, they are used in optical fibers where the evanescent waves actually flow across the fiber due to the TIR, and it can be used to extract information, and therefore this process is called eavesdropping. So this was the concept of evanescent waves, and we have covered the various uses and how the energy is actually flowing in the evanescent waves. Thank you.